Saat 16 ile 17 arasında Trox Multi-Service Shield BIM cihazları ve uygulamalarıyla ilgili bilgiler verilecek. Saat 16-17 arasında Yeniköy Toplantı Odası'nda katılmak isteyenler varsa eğer bunun da bilgisini vermiş olalım. Ve şimdi ise konuğumuz Mirco Becker. Onun hakkında size bilgiler vermek istiyorum. Forster & Partners gibi önemli mimarlık ofislerinde çalışmış, Frankfurt'ta Stadel Schule'de Architecture'da Architecture and Perfomative Design dersi veren Mirco Becker bizlerle Edimsel Tasarım adlı sunumunu şimdi sahnede bizlere anlatacak.
Thank you for having me here. It's really an honor. And sitting through today and yesterday's lectures, it's also inspiring to see what format you put together here. So I'm really, really honored to speak here. How do I start that? Okay. I'm going to talk briefly about performative design and building performative models. That is a different concept, or trying to kind of innovate on what we usually do as architects is producing drawings. And we are very familiar with the act of drawing, whether that's manual or whether that's in digital format. But the kind of problem is with drawings that information only accumulates slowly over time, and only we as architects have the knowledge and the capacity to forecast what happens to a particular move in a drawing further down the line. As we all know, building a building, finishing a building can take sometimes years, so we start with relatively crude drawings, and in the end, we hope that some building comes out of that. We take the client, a team along the way, and all put in this kind of incredible leap of faith that by the end there will be a product. So in performative modeling, what we're trying to do is to build a feedback, or more like an interaction between a model and the design. So the design process is something where the designer enters into a dialogue with its drawings, with its models, and the models feed back into the design process. That's in general the concept. I will go through 4 different examples at the same time as I go through these examples. It will also unravel some of the kind of digital innovations that happened over the last 15 to 20 years. Thank you for the introduction. I don't really have to go over that. That's just a short bio. I learned my craft, so to say, at Forster & Partners and KPFs in their parametric and computational groups. I worked for SARS and started teaching in the DRL, and for the last 3 years I'm teaching at the Städelschule and have my own practice in Frankfurt, in Berlin. And what I'm showing today is a mixture between academic and practice work, which always helps one to reflect onto the other. So the first performative aspect is a physical aspect. That's the easiest to explain. That was developed for a project in 2002 with my partner back then, Oliver Testmann, a design for a pavilion for the Athens Olympics. And as you see, it looks like a computer form, but it was actually designed in a physical setting. So it's a material process. We emulated the behavior of bending material. So it's literally just bending, in this instance, strips of perspex. In real scale, it would be a fiberglass lamellas. And we went through a whole iteration of forms. We digitized these forms, which you can see there. And these digitized forms then help to elaborate further on the actual architecture articulation. But the form was found through these physical models, and these physical models, as you can see, have a direct relation on the forces put into. So it's a different way than just drawing a form. It is a form creation where it is more analog to a crafting where you're in dialogue with the material itself. But obviously, you can also extract all sorts of drawings that are necessary to go through the normal moves of building a project, getting a project done. As I said, the project was initiated in 2002. It was done through physical models that were digitized, but there was back then no way to simulate that behavior digitally. Only in 2010, when friends and colleagues in Stuttgart at the ICD built their pavilion with a similar concept, they then had the means to actually simulate exactly that bending behavior. So they didn't really require any physical models anymore, but they could actually, in real time, test deformation of material physically and use that, again, as a design feedback. The next one is computational performance, which is the extreme opposite. So in this case, a project done last year, one of my students, Vasily, took on the algorithm that's used usually in medical imagery, where a field of data is taken to then actualize surfaces. So in an MRI scan, usually there's just a field of data values, and through common data values, a surface is created. So that's a technique that's developed like almost 25 years ago. And I studied that in 2006 for a conference and a little research to do kind of architectural design with that, and developed something like these nodes simply out of a computational process. And back then, there was no material relation to that. The only answer back then in 2006 was, let's 3D print it. So just push the button and 3D print whatever joint comes out of that. What Vasily did last year is that he found a physical and mechanical correlation to that process that is almost exactly the same as the computational model. So what he did, he started with ice cubes, and before freezing the ice, he inserted wires into the ice cube, and then put a current onto these wires. And because these wires then heat up, they create cavities, and these cavities are used for casting, first plaster cast, later epoxy cast in there. So it is exactly the same principle behind that as in the computational model. You take basically a heat value, and that heat value shapes the form. So you enter into that dialogue, and you've created, or what Vasily did, he created a corresponding model to the initial algorithmic concept. And then also realized that in a design proposal. A third performative aspect we went through is a mathematical one, started in 2006 with Computers and Fox Architects in London, where I worked in the computational group, and we developed for the Abu Dhabi airport a model to describe the entire building through a set of mathematical formulas and relations in order to have a good control of a fairly complex project. So that was the idea, that there is a certain undulation on the roof according to program and environmental conditions. And what we did, we defined a series of cross-sections and a mathematical formula how cross-sections and plan correspond to each other. So there's a series of cross-sections which in total are only 15 in the end. These cross-sections are aligned in the plan. And then the building basically generates itself. So that's no fancy animation. That really is just a time lapse how the building is generated onto these mathematical formulas and relationships. So you see how everything fits nicely together everything lands nicely onto the grids and so on, and it kind of zips together as it turns around. Still, what we can't take out is that it still takes an incredibly long time till buildings get built. Further down, there was additional detailing done, but all that detailing hang off the initial mathematical model. That was one of the earlier renderings. That's how the thing looks on site today. So the fourth concept, or the last one, I'm going to show is fabrication. Also, over the last couple of years, there is a great interest in digital fabrication. There's still great limitations on digital fabrication. We're hoping to 3D print stuff, but there's always, with architecture, is the problem of scale. So one thing we started to come up with in my studio is a process where we couple a 2D CNC cutting process with a 3D printing process. So taking these two concepts, the 2D cutting process is really good for handling larger pieces, handling flat pieces, and the 3D process at the moment is really good at tiny bits. So let's develop a system where we have flat sheets of material and we have a flexible node. So that node is not flexible in its behavior, but it's flexible on design time. Also, that node doesn't need any additional fasteners. It's snapping in. It's all snap connections. And what you can do, you can take any tessellation, whether it's triangles, quads, pentagons, and so on. You just figure out the node condition between those, and then you send one set of information to a CNC cutting device with a laser, water jet, and so on, and the other set of information goes directly to a 3D printing device. And then the only thing you have to do is snap these things together. So again, starting from the notion of fabrication in this sense and making fabrication a performative driver and embedding these two into a coherent model that updates itself on every design move. So as a summary, these four examples I showed, performative models are really a means of transferring knowledge through the design process. So as you start designing, you already have a feedback of its outcome and so on. And then you can basically start improving that as you increase the resolution and precision. It doesn't take away any of the usual moves you have in design, doing options, doing changes, embedding more knowledge, but it gives you a way that the architectural design, in that sense, becomes more of a prototyping exercise. Because in architecture, usually we have very little time to actually test how things turn out in the end. And this kind of performative approach brings it closer that we can perform these tests and behavior much earlier in that process. As an outlook or another critique is it should not be confused with current BIM models we have. BIM models are very much containers of information. They don't really model relationships, but we should strive, especially as designers, we should strive for models that set up really relation and help us to understand more about the actual outcome and behavior of the building as it's going to be built. I want to thank you for your attention. I want to point you to this latest publication of the school and my office if you're interested. Thank you very much.